Hello students, welcome to class 30. Okay, now we have gone with the next unit here, that is unit 2, that is oxidative addition. Oxidative addition. So reverse of this is reductive elimination. Reductive elimination. Okay, so this is what, and in the yesterday's class we had started with fluxional behavior. Okay, what do you mean by this fluxional behavior? We said that is a dynamic interchange of the atoms of maybe some atoms or all the atoms in the molecule, and you can see that the structure remains same, and we have learned regarding the Barry's pseudo rotation, okay, in the previous class, in the previous video. Okay, now if you see some examples, sometimes you can take this example, iron. Okay, like this. Okay, so this is very much you take any of this carbon. Now you can see here uh, like this. So you can see here this is neta 1. So iron is attached to neta 1, and this is neta 5. That is, iron is attached to all the carbon atoms, all the pi bonds here in this. Okay, now this can also be this can also what happens here, the fluxional behavior. See, if I name it here 1 2 3 4 5 carbon. So in the next case, so I can write in this way. So same thing I can write here. Okay, like this only, pentacarbonyl CO. See, so what happens here? So this is carbon 1 where the iron is attached. Now I will take it as a carbon 2 now here. So 3 4 5 1, like this here. That means what has happened here, now here whatever the hydrogen this is attached here, carbon is attached here, is at the one position, and here it is two position. Okay, so like this. In another case, if I go for another representation, I can take it 3 position, 4 position, 5 position, like this. So in one the metal is changing its carbon here from 1 to 3. Okay, very small, very fastly, and that is what we can see. This type of change we call as a ring whistling. Okay, ring WHIGG, ring whistling. So they will ask for 2 marks. So what is this ring whistling? Ring whistle means nothing but change in the rotation of the metal towards all the carbon atoms. Okay, that's a fluxional behavior, I can say, the molecule which shows the fluxional behavior here. So that is called as a ring whistling here. So we can judge that it's because of the same carbon here. So if you see at the high temperature, okay, at high temperature, same molecule, if you see at the high temperature, okay, of carbon 13 NMR study, you can see that there is one signal is observed. There is one signal is observed for 5 carbon here. Okay, so stating that the have the sigma bonded. Okay, once 5 carbon for which is bonded with the sigma bond. This is what happens when we go for the high temperature, at the high temperature. So there is fluxional behavior. Okay, so only one sigma, one signal is got into the of carbon 13. But if we lower the temperature at a low temperature, as yesterday I said you, if we lower the temperature, the interchange of the position becomes slow now. Okay, so this interchange, whatever the interchange I had shown you, this becomes very slow at low temperature. Okay, and the spectrometer is now able to catch hold of this change here, and we get different signals now, and we can detect which carbon it is been attached. So at low temperature different signal is got now. So a different signal is got, by which we can understand the nature of the metal, and which carbon heptacity it is been attached here. So this is how we can come to know. The best example to show this fluxional behavior is this compound, titanium hexa. Okay, so this compound in most of the case is shown by this compound. Okay, so we'll go for this like this. Okay, and like this. So this is a pentacarbonyl uh, compound CP4, which is attached to the central metal which is a titanium, and these two are neta 1, and these two are attached by neta 5, neta 5. See here. Okay, so this is neta 5, neta 5, neta 1, and neta 1. And now I can write this compound the same as I showed in the previous example. So like this, okay, this is neta 5 I can show here, and this I will show as a neta 1, and similarly here I can show neta 5, and here I can show neta 1. See here, so neta 1, neta 1, neta 5, neta 5. Now this has interchange here like this. So this has this will interchange here very fastly because of the fluxional behavior, and in one case you get here neta 5 now, and you get here neta 1. See here, and here also same thing, neta 5, and you get here neta 1. So the compound which was neta 1, neta 1 has become now neta 5, neta 1, and here neta 5 was there, it has interchanged to neta 5, neta 1. That means they are interchanging here. Okay, and this is how we can show the fluxional behavior of the compounds. Now same thing at high temperature, if you see at high temperature, if you see this compound, okay, so if you count the protons here, so all protons, if you count almost 20 hydrogen 20 protons you are going to get here. And just to do it, okay, count the proton, I have done it. So 20 proton if is there, so you are going to get one signal. Okay, you are going to get for one signal. Okay, if you take the NMR of this one signal, but if you go for minus 30 degrees centigrade, okay, at lower temperature, so you are going to get the two peaks here. So you are going to get two peaks. So this is how the NMR study helps us. Okay, so one is for neta 5 and one is for neta 1. So like this you are going to get two peaks at minus 30 degree at lower temperature. So fluxional behavior can be seen in the low temperature, but in higher temperature you can't judge it. So it's very fast, and you are going to get the single peak for 20 protons. So this is what you have to keep in the mind. Even if you take the graphical presentation, so usually I have taken here, so I will show here. So graphical presentation, you see here, so I have taken here of the same complex here, titanium. So see here, at low temperature minus 27 degrees centigrade, delta ppm NMR study, so you are going to get these two peaks here. See here. Okay, so one is showing neta 5, one is showing neta 1 here like this. Okay, but as you increase the temperature, this is from Hui textbook I have taken. So as you increase the temperature now, 10 degree, 20 degree, 30 degree, 40 degree, you can see here the peaks are broadened here like this. Slowly the peaks get broadened, and finally at 70 degree, 75 degree, you are getting single peak. Okay, so at low temperature minus 27, two peaks is observed here. Okay, which shows which shows the mode of binding here. Okay, but as temperature is increased, what will happen, the two peaks get broadened at 70 degree. So neta 1 gets vanished and a single peak is observed here in this complex. Okay, so this is what about you have to put that graph. Okay, so you can put that graph in the notes here. So like this, so like this, and finally you get like this. Okay, you can mention to minus 27 degree, 10 degree, 20 degree, 70 degree like this. So you can show that, and it is delta ppm, and this is in carbon NMR study. Okay, so this is how we can show that how the fluxional behavior is observed in most of the complexes. Is it right? And in one case there is hopping. No, if you take another case, that is the case where carbonyl hopping is take HOPPING, we get it as a hopping. Okay, or scrambling, SCRAMB LING. This thing you have to keep in the mind. Okay, whistling, hopping, scrambling. So they ask it for 2 marks question in examination or competitive examinations. What does this scrambling means or hopping means? So if you take this compound, okay, so this is usually always taken for this this one. I will take it here, carbon, bridge ring carbon, and again I will take here carbonyl compound this way. Okay, if you take this compound here and you mark this as label here with carbon 13, so what happens here in the next I can show it here in this way. So this carbon 13 will hop. Okay, in one, this one I will show you in one case. So like this, like this. So you can write here or carbonyl here like this, and here what will happen now, this carbon will come here like this here. Now whatever it was in terminal, it has come to bridged now. Okay, and finally from bridged again it will come to terminal here in the next last third. This is one. Okay, in another, this I can write it as what now, last it will come to here. So from 13 to here, from here to here like this. So there is carbonyl, this step, this we call as a carbonyl hopping or scrambling. Okay, the carbon monoxide from one iron to another iron gets interchanged here. So this carbon 13 is from this iron now, but finally we can see that the same carbonyl has went to another iron, so second iron C here. So this we have got it here this way. So there is interchange of carbonyl from one metal center to another metal center. Such type of this we call it as a carbonyl hopping or scrambling. Okay, so this is what about the one concept of the what to say fluxional behavior. Okay, now if I go for another example, there is a metal hopping also, so you can say that it is called a metal hopping condition. So this also is very much important examination point of view. If I take this 8 octacyclic compound, 1 2 3 4 5 6 7 8 something like that. Okay, and I put like this. Okay, so this is a first pi bond, second pi bond, third pi bond, and this is a fourth pi bond. Okay, what will happen here? So if I take this now like this, see here, and I will take it here, metal bonded with the ligands. See here, now it has bond with 1 and 4, so 1 and 4 pi bond. Okay, so this is what one thing. Similarly, if I take this now another 1 2 3 4 5 6 7 8 something like that, you can draw it properly. Okay, again here I will write 1 2 3 and 4. If I take it here, and now I can draw like this. Okay, so again here metal and this carbonyl. Now you can see here 2 and 3 I have taken here. Okay, so here I have taken second and third pi bond, second and third pi bond rotation like this. So see here, so like this only. Last one you can take it 1 2 3 4 5 6 7 8. Okay, like this. So I can draw in this way also. So this is one. Okay, 2 3 4. So here I can say 3 and 4. So here 3 and 4 pi bonds, here 3 and 4 pi bond metal is been attached. Okay, so either metal is changing its position, so not the ring here. So here ring is here kept almost here. So metal you can see here, so from this pi bond to this pi bond, this pi bond, this pi is changing, and such type of interchange we call it as what metal hopping. Okay, metal hopping conditions. So this is what about the one of the conditions we can say where we can show the condition whistling nature or the what you say the fluxional behavior of the compound. So this much with examples and explanation, I think for 2 marks the maximum they are going to ask for the metal fluxional behavior, so you can write it. Okay, so next concept of the unit 2 is oxidative addition. Okay, so this also we learn oxidative addition, reductive elimination. Okay, so what is this oxidative addition? Oxidative addition itself says that addition of the ligand. Okay, so there is addition of the ligand. When addition of the ligand is taking place, what will happen? There will change in the coordination number. Okay, there will be change in coordination number. So there will be change in electron count. This is electron count, and you can see that coordination number. Okay, electron count, and there will be change in oxidation number of the metal ion by 2 unit. This is very much important. By 2 unit means what? If oxidation number of the reactant is 1, so 1 plus 2 unit means that is plus 3. So oxidation number will be plus 3 upon giving the product like this. So this change by 2 unit, and even coordination number, if it is 14 in the product, it will be 16 like this. Okay, so this change by 2 unit case wherever we see, we call it as a oxidative addition method. Okay, and here if you have to keep in the mind, if the ligand if we add, okay, and it is not going to change the oxidation number, then it is not called oxidative addition. For example, if we take nickel dicarbonyl PPH3, okay, triphenyl phosphine TPH3, okay, and if I now here, what is oxidation number of nickel is 0 here, both are neutral ligands here. Now if I add a PPH3 here, again one more ligand if I add, so I am going to get PNI, okay, CO twice, PPH3 twice, this complex I am going to get. But since both are neutral, so again here it comes 0. So nickel is 0 0. So such type of conditions when the oxidation does not change here, so they are not called as oxidative addition. So this is not oxidative addition. Okay, so there should be, though it is ligand is added here, but there is no change in the coordination numbers. Okay, it has changed, but oxidation state is not changed by plus 2 unit. So such type of this we are not calling it as a oxidative addition reaction. Okay, and the reverse of this is called reductive elimination. So this is what also you have to keep in mind. For example, if I take this MLN here, okay, and add this ligand here, so what will happen now? Two arrows I can show. One is oxidative addition and one is reductive elimination. Now what I am going to get here is like this. So this is ln m, and x and y is going to add here this way. Okay, so this is what. So top if I go oxidative addition, so where x and y is added, and bottom if I go, it is the reductive elimination. So xy is eliminated, and again I am going to get different different compound here. Okay, so what will happen here? So here why this happens? Because this will take the electron like this. Okay, and metal has the electron here, so metal will donate the electron to this, and this will take electron and go away to form minus. Okay, and metal has donated the electron, so metal will get positive charge. Okay, and x is attached to this like this. Okay, now this positive charge is satisfied with the negative charge of the this ligand, and finally you are going to get this neutral complex. Finally you are going to get the neutral complex. So this is how the mechanism takes place here for the addition, for the oxidative addition here. So what are the conditions here? So that is much important here. What are the conditions for the oxidative addition? So first thing is what here, see here. So metal has to give the electron. That means metal should be rich in electron. So I will write here, metal should be rich in electron. That means rich in electron means low oxidation state. The metal should be have very low oxidation state. Okay, and they should be coordinatively unsaturated. Coordinatively, they should be coordinatorily unsaturated. Unsaturated means what? The coordination number should be less than 6. Okay, they should be less than 6, 2, 4, something like that. It should be less, like in this case we have taken 3 coordination number in nickel. See here, 2 plus 1 3, so from 3 it has gone to 4 now. So like this. So that is the reason why the unsaturated means less coordination number we have to prepare for this. Okay, so this is what about the first condition for the metals to be, that is they should be electron rich and coordinatively unsaturated, and they should have the low oxidation state. Okay, the metal should have the low oxidation state, so there should be ease in oxidation of the metal. That is very much important. Now second point about the ligands, if you take, the ligand should be spectator. Spectator ligand means what? You know that they will not take part in the reaction. So this type of this we call a spectator. Okay, so they are only helping for what? Electron density. Okay, so electron giving, so there is no role in this reaction here, but they only decide the electron density to donate it, and they make the electron rich also. Okay, so that's why electron donating group favors always. Okay, so they should give the electrons to the metal. So if metal is rich in electron, then definitely it is going to form the oxidative addition. That's why electron donating group ligand should be electron rich. So that thing is very much important here, so that it facilitates the metals metal ion to be in the low, get in the low oxidation state. So that is what. Now if you take the example like cobalt 1 or nickel 2 and iron, you take it as zero oxidation state. Okay, so cobalt 1, nickel 2, iron in zero oxidation state. Yeah. And if you go for the order of oxidative addition, definitely since it is low oxidation state, the iron will get more preference for the oxidative addition, followed by the cobalt 1, and lastly you can see that nickel 2 is going to have the oxidative addition. So this is what about the thing you have to keep in the mind. The next thing is what? Now if you go for down the group, that is your 3D, 4D, 5D. Okay, so 3D, 4D and 5D. So 3D cobalt. Okay, 4 it comes rhodium and iridium, like this. Okay, so if you go like this, so the way of the order of the oxidative addition here, so iridium is faster than the last one is cobalt. That is 3D is less here. Okay, so why the, as down the group the oxidative addition increases here, so iridium has a very good oxidation 5D because of diffused d orbitals. Okay, so and there is chances of increasing the coordination number. Okay, because of the big atomic structure here of the iridium, so coordination number expansion is very easy, and there will be diffused d orbitals also we can see in 3D orbitals. Okay, so but in 5D orbitals we cannot see that, but the increase in the coordination number we can see. Okay, so that is the reason why the down the group as we go, so you can see that there will be more chances of the oxidative addition reaction because of high coordination number. So for iridium has a high coordination number than the cobalt here. Okay, so that is the reason. So it has the expansion, and that's why the iridium becomes very good example for the oxidative addition compared to the rhodium and cobalt. Okay, this is what we have to keep in the mind, and that's why the best example of we learn is what Voskas complex. So what is this Voskas complex? That is iridium COCl PPH3 PPH3 twice. This is called your Voskas complex. Okay, so we can take this structure in this way: Cl PPH3 like this, CO, and here PPH3. So this is your structure for the Voskas complex. Okay, now if you add some now see what is the electron, what is the oxidation state of this. Here it is +1. Okay, +1, iridium is in +1 because chloride is -1. All these three are neutral ligands, and here -1 means +1 neutral. Now if I add hydrogen molecule here or water molecule, so what will happen now? The same compound is going to form in this way, IR. Okay, PPH3 twice will remain COCl, and this H2 is going to add for this here. In this H2 whatever I guys will add for this. Now if you see H means what? Minus charge, so -2, and this one 3, so it becomes a +3 now. See here. Now what happens now? Now oxidation state has increased from +1 to +3 now. See, that is change in what now? 2 units, +2 units. See, okay, even if you see coordination number also 1 2 3 4 coordination number, so 4 already is there, 4 5 6, so coordination number also has increased by 2 units like this. So that's why this is a perfect example for oxidative reduction, oxidative addition mechanism. So one thing you have to keep in the mind is D8 and D10. Okay, so these are very good configuration, electronic configuration for the good oxidative addition here. So why for D8? D8 means D8 is they are going to react faster for the oxidative reaction because of the square planar. Okay, complexes which are going to form for D8, and square planar means coordination number is how much? 4. Okay, so lowest the coordination number, fast is the oxidative addition. So that's why this is very fast. D10 why? So D10 why? Because of the electron rich. Okay, so D10 has a lot of electron in the metals, and that's why you can see that oxidative addition is faster in D10 also. Okay, so this is what about the oxidative addition here. Okay, now if you see ligands also. Okay, so if you see the ligands I have showed you, the electron donating ligands will always favor for the oxidative addition. Now if I go for titanium +4, so how will be the oxidative addition for titanium +4? Okay, if I take the complex of titanium like this, and if I go for different CH3, okay, or like this. Okay, Br. If I go for this complex, in fact, whether oxidation addition, because this is -1, this is -1, this is also minus, this is also minus, cyclopentadienyl. Okay, so 4 minus, so +4, so titanium +4, whether it goes oxidative addition. So no. Why it is not going oxidative addition? Because you can see here titanium, scandium, titanium is it is 3D 2 4s2, is it right? That means 4, so all 4 electrons is gone here, +4, that's why no electrons on the metal, and that's why you can see that this is not good, this is not good oxidative addition, so this will not undergo oxidative addition. That is D0, always you remember here. So D0 do not participate, so they are not undergoing the oxidative addition reaction, since they don't have any electrons, so it's not possible for the oxidative addition. So always the ligand should be electron releasing group. Okay, so that is what important. Okay, releasing group means electron density is increased on the metal, but if you take electron withdrawing group type of ligand, what will happen? That we call as pi acceptor ligand, so we call it as a pi acceptor ligands. If you take this pi acceptor ligands, electron withdrawing group, so what will happen? So they will decrease the rate of oxidative addition. So this electron withdrawing group will decrease the rate of oxidative addition reaction, because it makes the metal electron deficient. Okay, so that we know don't require for oxidative addition here. So that's why always this is preferred. So this is what about the concept of the oxidative addition reaction. Okay, so I think this is more than sufficient for this video. In the next video we'll learn a little bit more concept on this oxidative addition 1 or 2, and followed by the reductive elimination. Thank you.